All right. So in this video, I want to talk about the kind of macroscopic view of dielectric materials, what they do, and maybe some kind of experiments to sort of think about their various properties. And then in the next video, I will try to give a microscopic view of what's happening. So a dielectric is just a material whose charges are allowed to move around and adjust slightly. You might say that they can polarize a little bit. So I think it was Faraday who played around with this, and I'm not sure exactly what experiment he did, but let's do a kind of an abstract or kind of a cartoon experiment here. And let's imagine that we have a battery. Now the symbol for a battery is like this, and the larger side is the positive side of the battery. And let's imagine we have a capacitor. Okay, so the battery is just going to act to keep the voltage fixed. So we're just going to say V is fixed, right? And then what we want to do is imagine we have a slab of junk. A lot of times it really is just, it's like some junk. And we want to study what happens when we slide the stuff into the capacitor. So what Faraday found was the voltage is fixed. I mean, it's hooked up to a battery, it can't change. But in fact, what happens is that you get more charge on the plates. So you get more charge per unit volt, which means that the capacitance has increased. So he defined, or I don't know if he defined it, but we define the ratio of the new capacitance to the old capacitance. So we define kappa, looks like it's kind of a bendy K, is defined to be the capacitance, the new capacitance, so with dielectric, divided by the capacitance when it's filled with vacuum. Okay? So if you, so that's kind of interesting. Kappa is called the dielectric constant. Okay, the dielectric constant. And it just governs, it just tells you how much extra charge you're getting per volt. And it's the extra charge you're getting because of the presence of the material. Now, another way to think of this is as follows. Remember, capacitance is always proportional to epsilon naught. And epsilon naught is the permittivity of free space. So one way you might interpret this is as if everywhere you had an epsilon naught when the capacitor is full of vacuum, it's now being adjusted to have the appropriate permittivity for the dielectric material. So what's happening is you can think of this as replacing epsilon naught is replaced with epsilon, which is defined to be kappa times epsilon naught. So we would say you replace the permittivity of free space with the permittivity of, I don't know, rubber or something like that. And the permittivity of the material is the dielectric constant times the permittivity of free space. Okay, so that's one way to think of this. Trying to make sure I hit all the points. Yeah, that's okay. So one thing you can also say is if Q equals C times V, then, and what we're finding is that basically we're going to say that the charge with the dielectric constant is, so C is increased by a factor of K, so that means the charge with the dielectric constant is kappa E times the charge it would have had if it had been filled with vacuum. So that's kind of a simple little formula to remember. All right, let's imagine a different experiment. Let's imagine instead you charge up a capacitor, and so you charge up a capacitor and you have charge Q and minus Q on the two plates, and then you disconnect it. You don't hook it up to a battery anymore. In this experiment, the potential could change. The voltage is a constant, instead the charge is constant. So in this situation, the charge is constant, and what's going to happen is that if you were to insert a dielectric material, well, you can't add any charge because of charge conservation. Instead, what happens is that the voltage drop decreases. So we would have that the potential with the dielectric equals the original one divided by kappa. So it gets smaller by a factor of kappa. All right. So just a point of observation. When the response of the material is small, then, and kappas are pretty close to 1 for many things, then in fact, basically, you can solve all the problems ignoring dielectric materials. And the only effect, mathematically, of having a dielectric material in the problem is that at the very end, everywhere you have an epsilon naught, you can just erase it with an epsilon and just have an epsilon. So, for example, the capacitance formula, which was A epsilon naught over D, when you have a dielectric material, it just becomes A epsilon over D. The only effect of the dielectric material is to adjust the value of the permittivity. So you don't use the permittivity of free space, you just use the appropriate one for the dielectric material. Okay. Just one other thing. Sometimes, let me make sure I want to do this first. Yeah, sometimes people, instead of working with kappa, they write it as, now I'm afraid I'm going to get I always get the definitions messed up. I tell you what, I'll stop the video here, and before I proceed, there's a related quantity called the electric susceptibility, and I always forget little factors of how it's defined. But basically, it's the same as kappa. Instead, though, what the susceptibility does is it measures not the actual permittivity. Instead, it measures the deviation away from the vacuum. value. So, but it's basically the same thing. So next time we'll talk about that, and I will also try to give you more of a microscopic perspective on dielectric materials.